Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's lecture is an examination of current flow in balanced Y and delta configurations. Our objective is to examine exactly what really happens on a moment-by-moment basis in balanced Y and delta configurations with respect to current. This lecture operates under the presumption the viewer has more than a passing familiarity with the phasor analysis of balanced Y and delta configured loads, as illustrated in the three-phase AC examples lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. If you're at the same point I was when I was first introduced to three-phase AC circuit analysis, way back when the wild mullet still roamed the earth, you should be asking the same question I was. What in the hell is going on here? Yes, you can reliably perform Ohm's law and apply Kirchhoff's voltage law and Kirchhoff's current law to any and all Y and delta configurations, balanced or imbalanced, and get correct answers in phasor format. But really, what the hell is going on here? Where is current going? Where is it coming from? Where is it going to? Why is three-phase AC circuit analysis so important? These are the questions that kept me thinking long and hard until one day I got so consumed by them, I took the time to figure it out. In addition to thanks I've received in the comment section for posting these lectures, sometimes people ask me personal questions like, how come you're so funny? How come you're so sexy? And how come you're so smart? Undeniably, I am entertaining and sexy, but the dirty secret is I'm not that smart. I'm stupid enough not to quit. My instructors provided the guidance a young man with mediocre intelligence necessary to gain these skills, and I just wrapped around this advice, held on, squeezed it, and crushed it like a python eating a goat over the course of hours and hours of hard labor. It wasn't pretty, but I did eat the goat. One of the more tedious, yet worthwhile actions I took to really understand three-phase AC circuit analysis was to perform a step-by-step instantaneous analysis of balanced Y and delta configurations with a calculator, a pencil, and a piece of paper. Actually, a couple pieces of paper. Yes, it took a long time, but like I said, I was too stupid to quit. We are not going to do that today, but rather we're going to use the power of computers to quickly and directly arrive at numerical data and then sit back and take a look at the results. What you'll quickly realize is the same thing I did years ago. Current cyclically pulsates around and around balanced Y and delta configurations, and here's the necessary numerical proof for the hard-headed among you. I'll do the work so you don't have to. Sit back and enjoy the show. So we don't bog this lecture down in tedious calculations, let's use the results we obtained in three-phase AC circuit examples lecture. You recall, one of the illustrated example problems featuring a balanced 4-wire or 3-wire Y configuration and a 120-volt line-to-neutral, 208-volt line-to-line three-phase AC system with each branch impedance consisting of a 425 ohms at an angle of 40-degree load. In the course of our analysis, we learned impedance element Z1 drew 282.4 milliamperes of current at an angle of negative 40 degrees. Impedance element Z2 drew 282.4 milliamperes at an angle of negative 160 degrees. And impedance element Z3 also drew 282.4 milliamperes only at an angle of positive 80 degrees. I1 is defined as traveling into impedance Z1. I2 is also defined as traveling into impedance Z2. And finally, I3 is also defined as traveling into impedance Z3. You note each current through each balanced impedance is equal in magnitude and phase shifted from each other by a relative 120 degrees, as we'd expect for a balanced Y configuration. Additionally, we learned current in the neutral line for a balanced system would be 0 amps. Therefore, we don't need it. What in the hell does all this mean? Does this really mean three sources simultaneously dump 282.4 milliamperes of electrons into the center of the Y, and these electrons magically annihilate each other such that nothing comes out? Absolutely not. I must remind you that phasors are simply shorthand representations of sinusoidal quantities. Perhaps no fact could be more important, so it bears repetition. I say again, phasors are simply shorthand representations of sinusoidal quantities. What does 282.4 milliamperes at an angle of negative 40 degrees, negative 160 degrees, and positive 80 degrees really mean? You recall, phasor notation consists of two properties, the RMS value and the phase shift for a sinusoidally oscillating waveform. Plotted as functions of time, I1, I2, and I3 might look something like this. As an exercise to the viewer, I invite you to calculate the peak value of a sinusoidally oscillated waveform with an RMS value of 282.4 milliamperes. By all means, pause the lecture and do so now. If you're tracking, you should have obtained the following results. If you said anything other than 399.4 milliamperes, or square root 2 times 282.4, take the time to viciously smack the back of your hand with a wooden ruler. Peak values are always greater than RMS. RMS values are always less than peak. This means current can be expressed in the time domain as a sinusoidal function with a peak amplitude of 399.4 milliamperes times the sine of 360 degrees per cycle, times the frequency, or the number of cycles per second, times time, plus or minus the phase shift in units of degrees. The sine function in this case returns a value from positive 1 to negative 1 for an entry in units of degrees, not radians. As a means of checking our formula, consider the chain of unit conversion. 360 degrees per cycle times the number of cycles per second times time in units of seconds. Units of cycles cancel out, as do units of time, and we're left with units of degrees. And then add or subtract the phase shift, also expressed in units of degrees. I say again, this formula only works for units of degrees, not radians, nor a mix of radians and degrees, nor a mix of degrees and radians. If you want to use radians, number 1, you're an idiot. Number 2, you have to have your calculator set up to use radians, and number 3, you can't mix radians and degrees. It won't work, it don't work, and it can't work. We can now perform instantaneous analysis of these 3 time-variant current expressions by substituting a known frequency and desired time values. For the sake of simplicity, let's assume these waveforms all have a frequency of 50 Hz. Yes, I am well aware 120 volt line to neutral, 208 volt line to line light industrial 3-phase AC, commonly available in the US, has a frequency of 60 Hz. However, the period for a 60 Hz waveform is a rather ugly 16.7 milliseconds that doesn't evenly divide for the purposes of instantaneous step-by-step analysis. A 50 Hz waveform, however, is a cleaner 20 millisecond period that we can seamlessly divide into any degree of fineness we choose. For the purpose of this exercise, let's do 10 separate analyses in 2 millisecond increments. I'll demonstrate the procedure for the first couple, and then just let a computer do the dirty work. I1 as a function of time can be written as 399.4 milliamperes times the sine of 360 degrees per cycle times 50 cycles per second times time minus a phase shift of 40 degrees. Similarly, I2 as a function of time can be written as 399.4 milliamperes times the sine of 360 degrees per cycle times 50 cycles per second times time minus a phase shift of 160 degrees. Finally, I3 as a function of time can be written as 399.4 milliamperes times the sine of 360 degrees per cycle times 50 cycles per second times time plus a phase shift of 80 degrees. At t equals 0, we initiate our analysis. Substituting t equals 0 milliseconds into the time-variant expression for I1 yields 399.4 milliamperes times the sine of negative 40 degrees. Sine of negative 40 degrees, negative 0.6428 times 399.4 milliamperes yields roughly negative 256.7 milliamperes, where the negative sign indicates current is leaving impedance C1. Similar instantaneous manipulations of the time-variant expressions for I2 and I3 at time t equals 0 demonstrates I2 equals negative 136.6 milliamperes and I3 equals 393.3 milliamperes. This means 136.6 milliamperes is leaving impedance element Z2 and 393.3 milliamperes is entering impedance element Z3. Consider an application of Kirchhoff's current law at the central node. 393.3 milliamperes enters via Z3 and 256.7 plus 136.6 milliamperes leaves through impedance elements Z1 and Z2. 256.7 plus 136.6 equals 393.3 milliamperes, proving that what comes in has indeed come out. At t equals 0, I like to visualize line 3 dumping 393.3 milliamperes of current into the balanced Y through impedance element Z3, and all 393.3 milliamperes drains out of the Y through impedance elements Z1 and Z2, more of which flows through Z1 and less through Z2. Let's see what happens 2 milliseconds later at time t equals 2 milliseconds. Substituting 2 milliseconds into the time-variant expression for I1 yields 399.4 milliamperes times the sine of 360 degrees per cycle times 50 cycles per second times 2 milliseconds minus 40 degrees. Units of cycles and time cancel out, and we're left with 399.4 milliamperes times the sine of 36 minus 40 degrees, or negative 4 degrees. Sine of negative 4 is 0.0070. Negative 0.0070 times 399.4 milliamperes is roughly negative 27.9 milliamperes, where the negative sign again indicates current is still leaving impedance element Z1. Similar manipulations of the time-variant expressions for I2 and I3 demonstrates that at t equals 2 milliseconds, I2 equals negative 331.1 milliamperes, and I3 equals 359 milliamperes. This means 331.1 milliamperes is leaving impedance element Z2, and 359 milliamperes is entering impedance element Z3. Again, consider an application of Kirchhoff's current law at the central node. 359 milliamperes enters via Z3, and 27.9 plus 331.3 leaves via impedance elements Z1 and Z2. 27.9 plus 331.3 does indeed equal 359, again proving that what comes in has indeed come out. Similar to time t equals 0, at time t equals 2 milliseconds, I like to visualize line 3 dumping current into the balanced Y through impedance element Z3, and all of this current drains out of the Y through impedance elements Z1 and Z2, only this time, more of which flows through Z2 and less through Z1. Let's ditch the tedious manual calculations and have a computer do it for us. Subsequent analysis for the full 20 millisecond period and 1 millisecond time intervals reveals the following data. In the interest of expediency, let's examine every 2 millisecond step. If you want every millisecond, every half millisecond, or every femtosecond, be my guest and do this yourself. At t equals 4 milliseconds, 211.6 milliamperes is entering the Y via impedance element Z1. 399.1 milliamperes is leaving the Y via impedance element Z2, and 187.5 milliamperes is entering the Y via impedance element Z3. 211.6 plus 187.5 does indeed equal 399.1. At time t equals 6 milliseconds, 370.3 milliamperes is entering the Y via impedance element Z1. 314.7 milliamperes is leaving the Y via impedance element Z2, and an additional 55.6 milliamperes is leaving the Y via impedance element Z3. 370.3 does indeed equal 314.7 plus 55.6. At t equals 8 milliseconds, 387.5 milliamperes is entering the Y via impedance element Z1. 110.1 milliamperes is leaving the Y via impedance element Z2, and an additional 277.4 milliamperes is leaving the Y via impedance element Z3. 110.1 plus 277.4 does indeed equal 387.5 milliamperes. Okay, halfway there. At time t equals 10 milliseconds, 256.7 milliamperes is entering the Y via impedance element Z1. An additional 136.6 milliamperes is entering the Y via impedance element Z2. And 393.3 milliamperes is leaving the Y via impedance element Z3. 256.7 plus 136.6 does indeed equal 393.3 milliamperes. Time t equals 12 milliseconds, 27.9 milliamperes is entering the Y via impedance element Z1. An additional 331.1 milliamperes is entering the Y via impedance element Z2, and 359 milliamperes is leaving the Y via impedance element Z3. 27.9 plus 331.1 does indeed equal 359 milliamperes. At time t equals 14 milliseconds, 211.6 milliamperes is leaving the Y via impedance element Z1. 399.1 milliamperes is entering the Y via impedance element Z2, and an additional 187.5 milliamperes is leaving the Y via impedance element Z3. 211.6 plus 187.5 does indeed equal 399.1 milliamperes. At time t equals 16 milliseconds, 370.3 milliamperes is leaving the Y via impedance element Z1. 314.7 milliamperes is entering the Y via impedance element Z2, and an additional 55.6 milliamperes is entering the Y via impedance element Z3. 314.7 plus 55.6 does indeed equal 370.3 milliamperes. At time t equals 18 milliseconds, 387.5 milliamperes is leaving the Y via impedance element Z1. 110.1 milliamperes is entering the Y via impedance element Z2, and an additional 277.4 milliamperes is entering the Y via impedance element Z3. 110.1 plus 277.4 does indeed equal 387.5. Finally, at t equals 20 milliseconds, the process again repeats itself. Take a moment to think about what happened for this full cycle. Did you see what I did? If not, rewind the lecture to the beginning of the step-by-step analysis, turn off the sound, and turn up the speed. What you should see is current pulsating around and around the Y. Sometimes a large burst comes in one side, comes out two sides. Sometimes two smaller bursts enter from two sides, and a large burst leaves the remaining side. current through various branch impedances rises, peaks, and falls positively, and similarly rises, peaks, and falls negatively. Importantly, at all times, Kirchhoff's current law holds true, and what comes in does indeed come out. In this balanced condition, no current travels to the neutral line because there's no current to travel in the neutral line. That's why we removed it. As further proof, overlay the plots of current as a function of time with one another. During this time span, current comes into the Y through impedance element Z1. During this time span, current comes into the Y through impedance element Z2. During these time spans, current comes into the Y through impedance element Z3. Similarly, during these time spans, current leaves the Y via impedance element Z1. During these time spans, current leaves the Y via impedance element Z2. And finally, during this time span, current leaves the Y via impedance element Z3. What you get is this cyclical round and around we go, each phase experiencing the same rise and fall, but sequentially offset from one another, working in a coordinated fashion. Can you or can you not dig this on the same level that I do? Now is perhaps a perfect opportunity to remind you that in addition to being easier to generate and transmit, one of the principal advantages of three-phase AC is that it creates a rotating magnetic field. We'll examine electromagnetic interaction and the rotating magnetic field in greater detail in later lectures, but that's what just happened. If these impedance elements were motor windings, physically offset from one another by a relative 120 degrees around the stator of a motor, we'd expect winding 1 to experience some peak magnetic polarity, then winding 2, then winding 3, then 1, then 2, then 3, and so on. As a result, the rotor chases the stator rotating magnetic field around and around, and you get motor action. Alright, before we close up shop, let's take a quick look at current flow in balanced delta configurations, minus the lengthy preamble. We should experience a similar phenomenon, notably cyclically pulsating current at all times in accordance with Kirchhoff's current law. Recall during the three-phase AC examples lecture, available at the Big Bad Tech channel, we analyzed a balanced delta consisting of three impedance elements, ZAB, ZBC, and ZCA, each having an impedance of 425 ohms at an angle of 40 degrees in a 120 volt line to neutral, 208 volt line to line three-phase AC system. In the course of our analysis, we learned impedance element ZAB drew 489.4 milliamperes at an angle of negative 40 degrees. Impedance element Z2 drew 489.4 milliamperes at an angle of negative 160 degrees. And impedance element Z3 drew 489.4 milliamperes at an angle of 80 degrees. IAB is defined as traveling from A to B. IBC travels B to C, and ICA travels C to A. You will note current through each balanced impedance is equal in magnitude and phase shifted from each other by a relative 120 degrees, as we'd expect for a balanced delta configuration. Additionally, we learned current in the lines for this balanced delta configuration is equal to square root 3 times load current and phase shifted from the nearest load current by a relative 30 degrees. I1 equals 847.7 milliamperes at an angle of negative 70 degrees. I2 is 847.7 milliamperes at an angle of 170 degrees. And I3 equals 847.7 milliamperes at an angle of 50 degrees. I1 is defined as traveling into A. I2 travels into B. And I3 travels into C. You'll again note line current for this balanced delta is equal in magnitude and phase shifted from each other by a relative 120 degrees, as we'd expect. What in the hell does this mean? This most assuredly does not mean 489.4 milliamperes chases its tail around the delta, nor does it mean 847.7 milliamperes simultaneously pours into the delta from three different corners. These are phasor values and are merely shorthand representations of time-variant sinusoidal phenomenon. As previously, I invite you to determine the peak values for both load and line current for this balanced delta configuration. By all means, pause the lecture and do so now. If you're tracking, you should have obtained the following values. Load current will have a peak value of 692.1 milliamperes, and line current will have a peak value of 1,198.4 milliamperes, almost 1.2 amps. Let's again assume a 50 Hz frequency for the purposes of easily divisible instantaneous analysis. This means IAB as a function of time can be written as 692.1 milliamperes times the sine of 360 times 50 times time minus a phase shift of 40 degrees. Similarly, IBC as a function of time can be written as 692.1 milliamperes times the sine of 360 times 50 times time minus a phase shift of 160 degrees. And ICA as a function of time can be written as 692.1 milliamperes times the sine of 360 times 50 times time plus a phase shift of 80 degrees. Similarly, I1 as a function of time can be written as 1198.4 milliamperes times the sine of 360 times 50 times time minus a phase shift of 70 degrees. I2 as a function of time can be written as 1198.4 milliamperes times the sine of 360 times 50 times time plus a phase shift of 170 degrees. And finally, I3 as a function of time can be written as the 1198.4 milliamperes times the sine of 360 times 50 times time plus a phase shift of 50 degrees. Let us not dilly-dally with tedious manual analysis. Take it away, computer. Here's instantaneous current values for one full 20 millisecond cycle in 1 millisecond increments. To expedite this lecture, we'll examine this data in 2 millisecond increments. Let's take a close look at a couple entries. At t equals 0 milliseconds, negative 444.9 milliamperes travels through impedance element ZAB from A to B, where the negative sign really means positive 444.9 milliamperes of current actually travels B to A. Negative 236.7 milliamperes of current travels through impedance element ZBC from B to C, where again the negative sign really means positive 236.7 milliamperes of current actually travels C to B. And 681.6 milliamperes of current travels through impedance element ZCA from C to A. Similarly, at t equals 0 milliseconds, negative 1,126.5 milliamperes of current enters node A, where the negative sign really means positive 1,126.5 milliamperes of current actually leaves node A. Positive 208.2 milliamperes of current enters node B, and 918.4 milliamperes of current enters node C. Consider an application of Kirchhoff's current law at node A. 444.9 milliamperes of current enters node A through impedance element ZAB. 681.6 milliamperes of current enters node A through impedance element ZCA. And finally, 1,126.5 milliamperes of current leaves node A through line 1. 444.9 plus 681.6 does in fact equal 1,126.5. Similarly, consider another application of Kirchhoff's current law at node B. 236.7 milliamperes of current enters node B through impedance element ZBC. 208.2 milliamperes of current enters node B through line 2. And finally, 444.9 milliamperes of current leaves node B through impedance element ZAB. 236.7 plus 208.2 does in fact equal 444.9. Finally, consider an application of Kirchhoff's current law at node C. 918.4 milliamperes of current enters node C through line 3. 681.6 milliamperes of current leaves node C through impedance element ZCA. Finally, 236.7 milliamperes of current leaves node C through impedance element ZBC. 918.4 does in fact equal 681.6 plus 236.7. In all cases, what came in does indeed come out. Even when we don't concern ourselves with the internal workings of the balanced delta, but rather restrict our analysis to just the lines, Kirchhoff's current law holds true. If this is an unknown box with 3 lines leading to it, we could still apply Kirchhoff's current law. At t equals 0 milliseconds, line 2 dumps 208.2 milliamperes of current into the balanced delta at node B, and line 3 dumps 918.4 milliamperes of current into the balanced delta at node C. As a result, line 1 exhausts 208.2 plus 918.4, or 1,126.5 milliamperes from the balanced delta at node A. Let's dispense with Kirchhoff's current law analysis and examine subsequent 2 millisecond steps rather quickly. If you want to do it in 1 milliseconds and check these results using Kirchhoff's current law, be my guest and do so at any time. At t equals 2 milliseconds, 48.3 milliamperes of current travels B to A. 573.8 milliamperes of current travels C to B. And 622.1 milliamperes of current travels C to A. 670.4 milliamperes leaves node A. 525.5 milliamperes of current leaves node B, and 1,195.9 milliamperes of current enters node C. At t equals 4 milliseconds, 366.8 milliamperes of current travels A to B. 691.7 milliamperes of current travels C to B, and 324.9 milliamperes of current travels C to A. 41.8 milliamperes of current enters node A, 1,058.5 milliamperes of current leaves node B, and 1,016.7 milliamperes of current enters node C. At t equals 6 milliseconds, 641.7 milliamperes of current travels A to B. 545.4 milliamperes of current travels C to B, and 96.3 milliamperes of current travels A to C. 738.1 milliamperes of current enters node A. 1,187.2 milliamperes of current leaves node B, and 449.1 milliamperes of current enters node C. The time t equals 8 milliseconds, 671.6 milliamperes of current travels A to B, 190.8 milliamperes of current travels C to B, and 480.8 milliamperes of current travels A to C. 1,152.4 milliamperes of current enters node A, 862.4 milliamperes of current leaves node B, and an additional 290 milliamperes of current leaves node C. All right, halfway there. At t equals 10 milliseconds, 444.9 milliamperes of current travels A to B, 236.7 milliamperes of current travels B to C, and 681.6 milliamperes of current travels A to C. 1,126.5 milliamperes of current enters node A, 208.2 milliamperes of current leaves node B, and an additional 918.4 milliamperes of current leaves node C. At t equals 12 milliseconds, 48.3 milliamperes of current travels A to B, 573.8 milliamperes of current travels B to C, and 622.1 milliamperes of current travels A to C. 670 milliamperes of current enters node A, 525.5 milliamperes of current enters node B, and 1,195.9 milliamperes leaves node C. At t equals 14 milliseconds, 366.8 milliamperes of current travels B to A, 691.7 milliamperes of current travels B to C, and 324.9 milliamperes of current travels A to C. 41.8 milliamperes of current leaves node A, 1,058.5 milliamperes of current enters node B, and 1,016.7 milliamperes of current leaves node C. At t equals 16 milliseconds, 641.7 milliamperes of current travels B to A, 545.4 milliamperes of current travels B to C, and 96.3 milliamperes of current travels C to A. 738.1 milliamperes of current leaves node A, 1,187.2 milliamperes of current enters node B, and 449.1 milliamperes of current leaves node C. At t equals 18 milliseconds, 671.6 milliamperes of current travels B to A, 190.8 milliamperes of current travels B to C, and 480.8 milliamperes of current travels C to A. 1,152.4 milliamperes of current leaves node A, 862.4 milliamperes of current enters node B, and 290 milliamperes of current leaves node C. Finally, at t equals 20 milliseconds, the process again repeats itself. As previously, take a moment to think about what happened for the full cycle. Again, did you see what I did? If not, I'm encouraging you to rewind the lecture to the beginning of the step-by-step analysis, turn off the sound, and turn up the speed. What you should see is current pulsating around and around the balanced delta. Sometimes a large burst comes in one node, splits, and travels through two legs. Sometimes the outflow of two smaller legs join up, such that a larger burst comes out one line. Current through various legs and various lines rises, peaks, and falls positively, and similarly rises, peaks, and falls negatively. Importantly, at all times, Kirchhoff's current law holds true, and what comes in does indeed come out. As further proof, overlay the plots of line currents a function of time with one another. During this time span, current comes into the delta through line 1. During these time spans, current comes into the delta through line 2. During these time spans, current comes into the delta through line 3. Similarly, during these time spans, current leaves the delta via line 1. During this time span, current leaves the delta through line 2. And finally, during this time span, current leaves the delta via line 3. What you get is a cyclical flow around each corner of the delta such that each load in the delta experiences the same rise and fall but is sequentially offset from one another, working in a coordinated fashion. Again, can you or can you not dig this on the same level that I do? All other valid reasons aside, it's perhaps because of three-phase AC's innate ability to create a rotating magnetic field that three-phase AC is the primary power of choice for industrial systems and large generation facilities. Alright, hopefully this tedious walkthrough has clarified what exactly occurs inside balanced Y and delta configurations. Keep in mind this iterative analysis technique is not limited to balanced configurations, but can also be extended into unbalanced configurations as well if you've got the interest and motivation. All it takes is intermediate spreadsheet skills, or lacking a computer and spreadsheet software, a calculator, pencil, paper, and a couple hours to kill. Hopefully this lecture saved you some time. You've got a better appreciation for what phasor quantities truly represent in three-phase AC systems. In conclusion, this lecture examines step-by-step instantaneous current flow inside balanced Y and delta configured loads in three-phase AC systems. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.